Oh, so Basile is going to talk to us about snapshottable stores.
Oh, okay. But my okay, that's not the right one. No. Yes. Okay. Okay. Sorry for the technical problems. So I'm Basile Clément. I'm going to talk to you about snapshottable stores, which is joint work with Clément, Allain, Alexandre, Moine, and Gabriel Scherer. So my coders are academics. I work at OCamlPro, which is a small development and consultancy lab, where we, among other things, developed the Altergo SMT solver, which motivated some of this work. So what is this work? The problem we were trying to solve is that we are functional programmers. We are at ICFP. We love functional data structures, but sometimes we have to just bite the bullet and use imperative data structures. An example is actually the very implementation of the type systems we know and love, because many implementations of an efficient unification algorithm are going to use an imperative onion-find data structure. And issues arise when we try to combine these imperative data structures with algorithms that require backtracking. So for instance, if you have generalized algebraic data types in your language, you're going to have to introduce local equations, and you're going to have to backtrack those equations. And that can lead to a bunch of problems. Another example, as I said, is SMT solvers, where you're also doing a bunch of backtracking and you want to go back in time. So the solution, or at least the part of the solution we're going to look at, is that we are going to propose a data structure of a store, which is a bag of mutable references. We are looking at references because they are the basic primitive of imperative programming and mutability. And so we are going to have this API with a store type, and we are going to have all the usual reference operations, except that they all take a store as an additional argument. And this is good because it allows us to have a separate type of snapshots that we can use to capture the state of the whole store, the whole set of references, and restore it to whatever state it was when we took a given snapshot. This is just an API. We could imagine many different possible implementation of this. Here I have shown some of them with their asymptotic complexities. So the first row is just a imperative mutable references, where we have constant time get and set operations, and we of course don't have capture and restore operations. We could try to use functional maps for very fast capture and restore operations, because there is just nothing to do, so it's constant time. But then we pay a hefty cost of a logarithmic cost on each axis, which can quickly become expensive if you have a lot of these axes. We could try to use a vector to alleviate that problem and have the ability to copy the state of the data structure, but then that is a linear cost that we pay each time that we are doing capture and restore operation. Or we can just use our implementation, which is constant time for get and set axes and capture operation, and is linear in the restore operation, but only on the number of modification that you have actually performed on the references. And this is not just asymptotic complexities, right? If we run benchmarks, we can see here, this is an example in a type checker, the example that I mentioned before, where in the first column, the no backtracking case, we are typing a term that has no GADTs, and in the second column, we're typing a term that has GADTs, and so we do need backtracking. And we can see that the performance of map is fairly we pay a hefty cost when we go from just imperative references to maps in the no backtracking case. We are 4 times slower, which is a lot. And if we try to fix that with the vector, then no, in the backtracking case, this is just like not acceptable. And our data structure actually performs really well in this case. It's as good as imperative references if you have no backtracking, and it is still the same ratio with map in the presence of backtracking. So our contributions, and the way we achieve this is to propose this data structure, the store, a snapshottable bag of mutable references with persistent and semi-persistent APIs in the same data structure, a record elision optimization that enables us to have the same performance as imperative references in the no backtracking case, formal proofs using Iris and Coq, because the data structure that we get is slightly tricky to reason about, and we also have benchmarks. So what is this implementation? How do we do this? We first have to go back in time to 1978 to find the inspiration for this work, and the version trees of Henry Baker that used them initially to implement persistent arrays, to implement the environment of Lisp closures. And the idea of version trees is that if you have a data structure where you have multiple different states that you can work with, you can represent all of the states of your data structure as a graph, which is actually going to be a tree. And you're going to have one special node, which is d prime here in blue, which is, let's say, the current state of the data structure that you're operating on, and all of the other nodes are previous states, or maybe in the yellow part, those are like a parallel universe from the start of the data structure. But that doesn't actually matter. It's just other states that you have visited at some point in your history of interacting with the data structure. And we represent this with the current store in blue, we have the value, we have the other stores with the other states with also the value, and we have edges pointing towards the root, right? All the arrows are pointing towards the root ultimately, and each time you log the information about basically how to follow the arrow in reverse. If you are in the current state, how do you go back to the state C prime? Well, you just do the operation that is on the arrow. And this is nice because this means that if you have a snapshot, if you have a node somewhere that you want to go back to and you want to reset the state of the memory to that point, you just have to look at the path from that snapshot to the current node, and you can follow the edges in reverse, and you just flip everything around, and you get back to the state that you wanted to go, and you can even go back to the state that you started from, right? It's so this is fully persistent. And this is the rerouting operation, which is at the heart of all of this. So how do we actually implement this? Fairly similarly to what I just described. So we are going to have a node type that represents the node or the state of the data structure, which is just a reference to some piece of data. And the data is going to be either the mem constructor, which is a marker to say that, well, this state is represented by whatever currently is in memory. The values in memory are the right values for this particular node. Or it can be a diff node, which is an edge in the graph that I've just presented, where you have information about the reference that you're going to modify, the old value of the reference, and then a pointer to another node that will ultimately point to the mem node, the current node. We have an invariant on the store type that we have a mutable reference to the root, which is always going to be the mem node, and the snapshot is just a node. And in the same way, a reference is just a regular reference because we are going to write the appropriate value when we go through the different versions of the data structure. So get is, there's just a reference read, right? There's nothing to do because we are taking care by invariant. We point the store is necessarily the memory. We can just read the value from memory. Set is a little bit more involved. For set, we have to create a new node and record the current value of the node before updating the value of the reference, and we also have to maintain the invariant that the store has to point to the new node, because we have modified the memory, and so we have to update the store to keep track of that information. There is one issue with what I've presented so far, and it is, if you just look back at set for a minute, we are always creating new versions of the nodes, right? And that is not very good. This is never going to be as efficient as the pure mutable reference implementation that I've shown in the beginning, and that's because there's something we can do with the API that I've proposed, with explicit capture and restore of the snapshots, which is, we know that if a node was not captured by the user, it's never possible to go back to that specific state, right? So here in this graph, we have some nodes that have been captured by the user, but we also have nodes that are inaccessible. And we can probably try and avoid materializing those nodes and those edges. And this is exactly what the record elision optimization does. We are going to have some markers, and I'm not going to go into detail into how exactly we implement this. This is explained in the paper. But basically, we are going to have a generation counter that we increase each time we take a capture. And when we do a set operation, we are going to check if the generation associated with a reference, which is the generation of the store the last time it was written, if it's the same as the current store, then we know that we have already recorded the old value somewhere, and we have nothing to do. We can just perform a regular write. And otherwise, we do the same thing as before and record the old value. This is the full implementation. You don't have to read it right now, but it's just to show that it fits in one slide. It's a little bit tricky to reason about, and this is the thing that does not fit on one slide, right? This is the formal proof, which we have written using Coq and Iris, and we have everything that I've presented so far is in the proof. Snapshot the stores, the rerouting, the record elision. There are some bits and pieces that I didn't talk about that are not in the proof, but we have a monolithic predicate for the store that says that a store represents some functional state, and this is an affine resource. Ideally, we would have wanted to have linear types for our stores, but that's not available in the programming language we use. And we also have a snapshot predicate, which is this time is persistent and can be reused as much as you want. This is one insight from the proof that I want to share, because I think it's interesting and kind of relevant. The idea of the proof of record elision is that we can create a smaller graph that only includes the captured nodes and the current nodes. And in fact, in the semantics of the data structure, from the point of view of the user, we only care about those sort of like big edges from between those like big nodes, those nodes that are captured or current nodes. And we don't actually care about the intermediate nodes. And in the proof, we are going to be able to say that, OK, as long as we preserve the right semantics for those arrows between the captured and the current nodes, then we can change a little bit the semantics of the inner nodes, and it's not going to impact anything. We also have some high-level wrappers. Like we have the full, you can use the full power of the snapshots in your program, but you can also say, OK, I'm going to do things a little bit simpler, and we have those two wrappers that are actually implemented using a semi-persistent version of what I've presented so far, so they are a little bit more efficient. And we have a wrapper that will try to do things, and then if you raise an exception, it will reset the state to what it was in case of an exception, and if you succeed, it will proceed with whatever modification you've made. And we have a temporarily wrapper that will take a function, run the function, and then reset the state, whether there is an error or not. And this is useful to, for instance, in solvers, check if something is true, and then without performing any modifications. And that's basically the end of the presentation. There is more. There is OPAM package. You can install it using OPAM. You can try it. You can play with it, and I encourage you to do so. There are some more things that I didn't talk about in the paper. So there is this transactional API for semi-persistence, which is similar to the persistent API, but like allows sort of more performance when you don't have to go back to a specific state. There are some tests using Monolith, which is a framework for differential testing, which was really invaluable during development. For us, it was almost like having an oracle when we were developing features. Like you wrote the new feature, you compared it with the test, and if the test passed, you were like it worked essentially. So that was really nice. There's some discussions about trade-offs and design decisions. Especially around liveness, which the data structure I've presented has very good liveness properties because we only point towards the current state of the root of the store. So if you just forget some snapshots and stuff like that, then there are just going to be garbage collected. We have benchmarks. We have, of course, some more references to related work and stuff. And there are some future work that we want to do. One is that we want to have some sort of snapshottable point to in separation logic so that you can port your proofs from imperative code to work inside the store. And this is some work we have started to work with François Potier. And there are also some things that need to be taken care of around having some custom data structures in the store. The main point being that if you have a data structure that makes use of amortized analysis, like a hash table or a redimensionable array, it's not going to work very well to snapshot that. And you want to have sort of those amortized operations outside of the store. And that's the presentation. Thank you for attending.
Yep.
Hello, Adam Chapala from MIT. You have a fixed interface for working with the mutable state here where the library sees traditional reads and writes of single reference cells. I would think in a lot of cases, if you had a higher level API that works with higher level operations, you could improve the performance a lot. Have you considered generalizing in that way?
Yes, so this is a little bit what I'm talking about with this custom data structures. I think that in a lot of cases, you can sometimes improve the performance by logging the basically the operations at a higher level for the data structure you're doing. But this is first not necessarily going to be more efficient because it's going to be more complex operations. Those are going to be more complex to undo. And also, one of the things that we wanted to do with this implementation is have something that is dead easy to use, basically. You have your imperative data structure, you replace the use of mutability with the references, and then you get something that is going to work and that is going to have reasonable performance. Right, and then if you want to do something hyper-specialized, then, okay, you have more work to do, but we're fine with that.
If you're just thinking about an SMT solver where the units of rollback would typically be full assertions of big logic formulas that might involve a lot of allocation, it just seems natural to take advantage of that somehow, but maybe in practice it doesn't.
Yeah, so you can still have stuff that is not in the store, right? So you don't have to use these references for all of your data structures, right? So you can pick and choose the things that you actually want to backtrack, and then the things that you want to keep, you don't have to use that.
Thanks.